Okay, so the first chapter is temperature. You all have a sense for temperature. Temperature tells you how hot an object is. Okay? And we'll give a technical meaning to that phrase. When we say how hot an object is, we'll tell you exactly what that means. Okay? All right, so let me actually start off by showing you a little okay, so this is for a gas. So this is just a simulation. As you see, okay. So you can see this gas is at 30 atmospheric pressure. Okay. What is the pressure in this room? 1 atmosphere. Okay, so this is 30 atmosphere. It's quite a high pressure. Okay. And the temperature is 300 degree Kelvin. Okay. So now let me warm the gas. I'll raise the temperature, and you tell me what's happening. Okay. Look at the molecules. What happened? I'm sorry? What do you mean excited? They were moving faster. That's what temperature tells you. Okay. A temperature is a measure of the average kinetic energy of the gas molecules. Okay. So if you double the temperature, the average kinetic energy doubles. Okay. Well, so this I showed you this for a gas molecule. What happens to a solid?
It would melt.
Well, if it didn't melt, can I raise the temperature of this table without melting? So what happened there?
They're just vibrating, but in a way that they stay solid. I guess.
Very good. You can just vibrate with a larger amplitude. Okay. You can attach a mass to a spring. Okay. And the mass doesn't have to come off the spring. You can increase its energy. If you give it a larger amplitude, its speed will increase. Its average kinetic energy will increase. So that's what temperature is. Okay? It measures the average kinetic energy of the molecules. Okay? So here's an amazing thing. What's the temperature of the gas in this room? It's about 20 degrees Celsius, 300 degree Kelvin. What's the temperature of this table?
About the same.
It's
Is it
exactly the
Yeah.
same, yeah. So the average kinetic energy of these gas molecules is the same as the kinetic energy of these molecules, of the molecules on the wall.
The same.
The same. The molecules in the chair,
The same.
same. For every inanimate object, it's the same in this room. Okay? All right, so we had a sense for temperature. Now we are sort of giving technical meaning to stuff. Okay. All right. So the first 4 chapters in this course form the subject of thermodynamics. Okay. In the first chapter, we'll define temperature and heat. Then in the second chapter, we'll talk about kinetic theory of gases. I showed you a model of the gases. So we'll relate, so for one of the big results will be to relate the average kinetic energy to the temperature of the gas. Okay. We'll relate the average kinetic energy to the pressure of the gas. Okay, and so on. So we will relate the microscopic properties. Have you ever seen a gas molecule? No. We'll relate the properties of a gas molecule to the pressure that you can measure using a macroscopic instrument. Pretty neat. Okay? So that's what that chapter will be about. Then we'll talk about the next chapter will be the first law of thermodynamics. The first law of thermodynamics is a conservation of energy principle. except that now we'll keep track of heat as well. Okay. And then the second law of thermodynamics. So for instance, okay, if you have 100 joules of kinetic energy, let's say you're driving your car and your car has kinetic energy, there's so much kinetic energy. If you apply brakes, what happens to that energy?
It's transferred to the ground.
Okay.
Friction. Heat.
It all gets converted to heat. Okay? When your car stops, where did that energy go? It got converted all to heat. So you can convert 100% of kinetic energy to heat. You can convert all of it to heat. Try going the other way. When you try and go the other way, well, the second law of thermodynamics tells you what is the limit. Okay? In your car, what is your car, by the way? It's a heat engine. What do you mean by that? What does, yep.
Like it produces heat from the engine?
Well, so a heat engine, what it does is it converts heat to other forms of energy. That's what a heat engine is. What does your car do? It converts heat to motion, to mechanical energy. Okay? That's your car. Yeah. Now, of course, so do you guys know the efficiency of your car? 20%. Okay, what does that mean? Every time you put $5 of gas in your car, you get $1 of motion. What happened to the other $4?
Lost his heat.
You threw it out the window. That's not even the punchline. It gets worse. Do you want to hear the sad story? Okay, let's hear the sad story. You'll be so happy to get in your car. What's that?
I said, just rip the Band-Aid off. Tell us the sad story.
All right, all at once. So here's your car, okay? And I'll, since I'm not good with numbers, I'll make it easy on myself, okay? What's your goal when you get in a car? If you want to get from point A to B. So I want to transport this 200 pounds of mass from point A to B. And I put this 200-pound mass in this 400-pound object, 4,000-pound object. Okay? Let's say, to keep it simple, I'm spending 100 joules of energy. Okay? Remember, I released 100 joules of heat by burning gasoline. I got 20 joules of energy out of it. And that was transporting this guy, but I only wanted to transport this guy, which was 5% of that. So 5% of this is 1 joule. I spent 100 joules to accomplish what I needed for 1 joule. Every time you get in your car, you're accomplishing 1% of what you spent. Is it crazy? It's crazy. But we do that all the time. See, we're cooling this whole building for 20, 30 people. So this kind of stuff is all over the place. Okay. All right, anyway. So the second law of thermodynamics, okay, will tell you, one of the things it will tell you is how much heat can you convert to work. Okay. All right, so these 4 chapters will become a whole course. in your junior senior level, the thermodynamics course, the favorite course of all engineers. I'm being sarcastic there. Okay. All right, so now you know what temperature measures. Okay, it measures the average kinetic energy per particle of the system. Okay. There are 4 laws of thermodynamics, and we'll talk about them. Here are the 3 commonly used scales for measuring temperature. Yeah. The Celsius, Kelvin, and Fahrenheit scale. Yeah. When you heat something, so when I heat this table, what happens? If I raise the temperature of this table, what happens?
The average kinetic energy of the particle in there.
Increases, its dimensions also increase, ever so slightly. But that'll matter in practical situations. Okay? So we'll talk about that. So thermal expansion, and then we'll talk about heat and the form of energy. So as David had mentioned, see, here's a little diagram of, you can think of this as the table. This end of the table is hot, and this end is cold. And you can see that even though these atoms are at fixed location, when this end of the table is hotter, it's vibrating with a greater amplitude. So these guys have greater average kinetic energy than these guys. Okay? All right, and heat can be transferred via conduction. So we'll talk about this later in the chapter. But what's happening is, see, these guys are vibrating with a greater amplitude. They'll bump into their neighbor. They share some of this energy. Then these guys bump into their neighbor, share some of the energy. These guys lose energy. These guys gain energy. And how long does this keep happening?
Continuously, it just keeps happening on and on. Until everything is the same.
No, exactly. Okay. All right. So it keeps happening till the temperature becomes even everywhere. Okay. So this would happen in all kinds of phenomenon. Let's say we go to that corner and make a pile of your physics books and burn them. What will happen? All that heat will spread evenly. Okay. So until you reach equilibrium. You know. When the temperature is even everywhere, does exchange of heat stop?
No, but it just gets passed back.
Very good, my friend, very good. All right, so there is no net exchange of heat. Okay, there's still exchange of heat happening. Okay. All right. So thermodynamics is a branch of natural science concerned with heat and its relation to energy and work. Okay. So, I mean, one of our goals, the way this subject started was, I mean, you had steam engines and stuff like that, and how much work could you get out of them? Okay. It's the rules of thermodynamics apply to systems of many particles. Yeah. What do we mean by many particles? 10, 15? So when we say many particles, it applies to systems. You have to have Avogadro's number, a lot of particles. You can't apply it to 1,000 gas molecules. So, and what is Avogadro's number? I'm sorry? Yeah, what is it? There you go. So 10 to the 24 number of particles. Yeah. So you have to have a really large number of particles. Okay. So a thermodynamic system is a system which contains a lot of particles. Okay. Can you give me an example of a thermodynamic system? The table, the gas in this room, you are a thermodynamic system. Okay. So, yeah. Now it turns out that we can apply, all these rules are useful in a wide variety of areas. heat engines, phase transition, chemical reactions. If you want to understand any of these phenomena, okay, you have to understand thermodynamics. Are essential for chemistry, chemical engineering, and all that. Yeah. And even in economics, rules of thermodynamics have been used. Okay. So by the way, 1 mole of gas at standard temperatures, what is the volume occupied by 1 mole of gas?
22.4 liters.
22.4 liters, that's about 4 gallons, 5 gallons. So it's, you know, roughly about that dustbin. Okay. So there's about, I would say, 1,000 to 10,000 moles of gas in this room. Okay. So there's 10 to the 28 molecules in this room. All right, so here's an amazing fact. There's 10 to the 28 molecules in this room. And when I ask you the properties of this gas in this room, what is it that you're going to tell me about the gas? You're going to tell me its volume. You're going to tell me its temperature. You're going to tell me its pressure. You're going to tell me 4 or 5 properties. Okay? So what we'll be doing is studying thermodynamic systems in equilibrium, and the state of the system can be characterized by a handful of numbers. Okay? Now, of course, remember, if you burn your physics pile of books, what is happening? Heat is flowing all over. Okay. Now, that's the temperature is varying with space and all that, and that's not an equilibrium situation. That's dynamic. Energy is moving. Okay. We can learn to describe that, but then you can't characterize the system by a few numbers. You need more numbers. Yeah. But we'll be studying systems in equilibrium. You guys understanding this? And we'll be characterizing the system with just a few numbers. Yeah. So here are the 4 laws of thermodynamics. Yeah. The 0th law says that in thermal equilibrium, says systems which are in thermal equilibrium with each other are at the same temperature. Yeah. So thermal equilibrium means when 2 systems are not exchanged, there's no net exchange of heat, then they're at the same temperature. Yeah. Can you tell me what are in thermal equilibrium in this room? Everything? I hope you're not in thermal equilibrium with it.
Everything that's in room, that's like the room temperature. same temperature.
That's inanimate. So hopefully David is not in thermal equilibrium with this chair, right? So is this table in thermal equilibrium with the wall?
Yes.
Is it in thermal contact with the wall? Okay, what does thermal contact with the wall mean? Just when you're in thermal contact, you can exchange heat. Okay? So can the table exchange heat with energy with the wall? Yes, it can. Electromagnetic radiation. Okay? Everything is in thermal contact with everything else. The strength of the contact might be different. I'm in thermal contact with this table. The thermal contact just became stronger. Okay? All right. You guys following this? Yeah. All right. So the first law of thermodynamics, it's conservation of energy principle with heat included. Okay. So it expresses the existence of a quantity called internal energy of the system, and shows how it's related to distinction between energy transfer as work and energy transfer as heat. Okay, let me illustrate that. Okay, so when I grab onto this bottle, I'm transferring energy from me to the bottle via heat. I can also lift the bottle up. I transferred energy from me to the bottle, except that now I did work. Okay? So there's various ways of energy transfer, and then we'll talk about that. Okay? So the second law of thermodynamics expresses the existence of a quantity called entropy, which measures the disorder in the system. Okay? And okay, so that's related to how much work you can extract out of a heat engine. Okay? And it turns out that the entropy of an isolated system never decreases. Yeah. So disorder in an isolated system always increases. Yeah. So here's a mystery, sort of mystery of life. A biological system. Here the entropy is decreasing, disorder is decreasing. As you grow and stuff like that, as a biological system grows and develops, the disorder is decreasing. You're arranging molecules in a more orderly fashion. So if this was the system, if the disorder here decreased, what does that mean? The total disorder has to increase. So the disorder in the environment grew. Okay? So anyway, so we'll talk about entropy. That's, again, this is a separate chapter. This one is a next chapter, this is the next chapter, and so on. Okay? The third law of thermodynamics implies that it's impossible to cool a system to exactly absolute zero. What is absolute zero?
No
Yeah.
motion?
Yep, exactly. So these are the gas molecules, and as you saw, if I heated this gas, the molecules their kinetic energy increased, and if I cool the gas, their kinetic energy would decrease. Okay? And what is the best I can do? I can stop them all. Okay? And when I stop all the gas molecules, you will have reached 0 degree Kelvin, and that's absolute zero. Okay? So temperature is a measure of how hot an object is. It's a measure of average internal random kinetic energy per particle. All right, so let me elaborate on that. Okay, so the temperature of this object measures the random internal kinetic energy of these particles. Okay. Now, I added kinetic energy to every particle, but that didn't increase the temperature. Okay? So it's a measure of the random kinetic energy. All right, so when the universe began 14 billion years ago, the temperature was about 10 to the 39 degree Kelvin. Today we are bathed in a cosmic microwave background radiation. This is microwave radiation, so So what that is saying is, if this is a universe, we are bathed in photons, and the temperature of these photons is 2.7 degree Kelvin, okay, 2.73 degree Kelvin. This is the cosmic microwave background radiation, and the wavelength of this radiation, the peak, the most common photon is about 2 millimeters. Okay, that's the wavelength of this radiation. And we'll talk about it hopefully in the future. All right, that's what this is, this statement is. Okay? So today the temperature of the cosmic microwave background radiation is 2.7 degree Kelvin. Let me show you a picture that I'm sure everybody has seen. So this is the picture that we are talking about. You guys have seen this? Okay. So the average temperature is 2.7 degree Kelvin, and what this is showing you is the fluctuations from that temperature. And the red spots are 200 microkelvins above the 2.73 average degrees, and this is below that temperature. Okay. And this measurement won the Nobel Prize. Do you guys know why it was important to measure this? Okay, so in the 1970s, they had measured this, and the temperature was even 2.73 degree Kelvin, or whatever that number is. Okay? And then they had to look hard for these fluctuations. It was a harder measurement. But measuring this fluctuation was important. Why do you think so? The colder areas, that's where the galaxies form. These are empty spaces. You're around, we live in a galaxies, so if you didn't have these colder spots, that's where the galaxies form. Okay, so it was extremely important to find that. All right, anyway, we'll talk about it more, okay? So 2.725 degree Kelvin is the average temperature. Yeah. So thermal contact, you know what thermal contact means now? When are two objects in thermal contact?
When they can exchange heat.
When they can exchange heat. What are the three mechanisms for exchanging heat? Right. So you can exchange heat by any mechanism. Okay. So if you can exchange heat, then you're in thermal contact. And of course, the strength of the thermal contact can vary, okay, for the same two objects. So you can exchange heat via these three mechanisms. Thermal equilibrium. What does thermal equilibrium mean? Mm-hmm.
That there's like no heat energy exchange, like
No net heat energy. Yeah. Okay. So when you're in thermal equilibrium, there's no net exchange of heat. That would mean that you're in at the same temperature. Okay. Two bodies in thermal equilibrium have the same temperature. Okay. So the zeroth law of thermodynamics states the obvious. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then they're all at the same temperature. Okay, so that's the zeroth law of thermodynamics. Okay. And why is it called the zeroth law of thermodynamics? Well, you came up with the first law and the second law, and then for logical reasons you had to state this, so we called it the zeroth law of thermodynamics. Okay. So it was an afterthought. Okay. So let me show you an amazing thing. Okay. David, come here. Touch this object. Touch that on. Which one is colder?
Well, this feels colder,
Right.
but
Which is colder?
neither.
So why does that feel colder?
It's
Huh?
conducts better, right? It's metal.
So this is not a good thermometer. Okay? It doesn't, this thermodynamic system is not a good thermometer. So what's he sensing?
One material can draw heat faster than the other.
So what he's concerned about is he's got a finite source of energy, finite amount of energy. He's worried about his energy loss. So you are more sensitive to energy fluxes. Okay? Thank you, Dayton. And that's what this statement is. Okay? Humans are to a large degree sensitive to energy fluxes rather than temperature. Okay? So if you're an outhouse in a mountain cabin equipped with a wooden and a metal toilet seat, you can tell the difference without. Okay. All right, so now we'll talk about the temperature scales. There are 3 commonly used temperature scales. It turns out that you can make an infinitely many temperature scales, but these are the 3 commonly used temperature scales. Okay, so here's what this thing is based on. So it turns out that physical phenomena happen at the same temperature. So for instance, ice will always melt at the same temperature, assuming 1 atmosphere pressure and all that stuff. You can melt it at night, day, today, 10 years from now. When ice is melting, you can put your finger in there, and it'll always feel the same. So it's happening at the same temperature. Okay? So to make a temperature scale, all you need is 2 phenomena, physical phenomena, happening at different temperatures. So for our common temperature scales, we'll take melting point of water and boiling point of water. Okay? And like I said, if you do this at 1 atmosphere, okay, those 2 things will happen at the same temperature, no matter when you do it. Okay? And now to build it, and of course, this is warmer, and this is colder. So to build a temperature scale, you can call this anything you want. This anything you want. So the Celsius folks call this 0 degrees Celsius, and that point 100 degrees Celsius. So if you wanted to come up with a new scale that is 10 times finer, what would you do?
You could make the ice point 0 still and make the steam point 1,000.
There you go. All right. So you can do anything you want. Okay? So the Celsius people call this 0 degrees Celsius, that 100 degrees Celsius. The Fahrenheit people call this 32 degrees Fahrenheit, 212 degrees Fahrenheit. And you can see that there's 100 degrees here. There's 180 degrees here. So this scale is more sensitive. Okay, or it has more divisions in there. Yeah. Look at this guy, Kelvin scale. This has got 100 degrees between these 2 points. Yeah. So it seems like this is redundant.
Celsius, but they move 0 to absolute 0.
Right. So here's why we came up with this. Okay, so we had this scale, and then once we realized that there was a lowest temperature, when was the temperature? What is the lowest temperature you can reach? And when everything comes to a standstill. And in this scale, it's minus 273 degrees Celsius. Tell that to your little brother, right? Minus 273 degrees is the lowest temperature. So you just invent a new scale and call it 0 degree Kelvin, that's all. Okay? So that's, all right, so to make a temperature scale, all you need is two physical phenomenon. Okay? This is the boiling point of water. This is the melting point of ice. Okay, this happens at 1 atmosphere. The pressure fluctuates. You could go to Denver. As you go higher, the pressure is lower and water boils at a lower temperature and so on. Okay, so you want a more precise control point, a phenomenon that happens at one point, no matter where you are. And so these are the 2 points that are used for technical reasons. Triple point of water, and we'll talk about that in a second, and absolute zero. Absolute zero is very well defined. You can be anywhere in the universe. Okay? There could be places in the universe where there's no water, and then so how does that person understand? Okay? Those scales. Okay, so absolute zero, everybody understands, and the triple point of water, so you got to have water there. Anyway, the triple point of water. Okay, so we'll come to this guy in a second. Here's the triple point of water. Okay, so here's a phase diagram, and this is important, very important. So you have phase diagrams for all kinds of substances. And what does this tell you? What is this telling you? Yep.
Pressure versus temperature, like what form the water's gonna be in?
See, so exactly. So this guy, this one diagram has a lot of information. So this substance H2O can only be in 3 phases: solid, liquid, and vapor. And for these 2 thermodynamic parameters, so for this pressure and this temperature, it can only be in water phase. For this pressure and this temperature, it can only be in vapor phase. For this temperature and this pressure and this temperature, what is that line telling you? If you're anywhere along that line, what does that mean?
It could theoretically be either or both.
Yeah, it can coexist. That's what that is. Okay? So if you're anywhere along this line, water and vapor can coexist. Okay? So where are we right now? Hmm?
We're in the section for water.
We are somewhere along that line. Okay, we are here somewhere. Okay, no, here. So water, vapor. Okay, this is the boiling point. Okay, the temperature is 22 degrees Celsius. Okay, so this is okay. All right, I'll have to come back to that one. Okay, so it's the partial pressure. Okay. All right, so let me tell you something else about this. Okay, so here's a coexisting curve for solid and liquid. Okay, and the slope is negative. Okay? For most substances, the solid liquid coexistence curve is positive, has a positive slope. Okay. So for water, this is a negative slope. And here's an interesting fact, okay, because of this. All right, let's start off with, so this is 0, this is 0.1 degrees. So let's start off with ice, okay, at 1 atmosphere at minus 5 degrees Celsius. Okay? So you can have snow on the ground at minus 5 degrees Celsius. Okay. You guys ski, right? Or you guys know about skiing if you haven't skied. So how does that work? Okay. So here's snow at 1 atmosphere. Okay. You step on skis, you put on skis, and now the snow, the pressure is increased on the snow. That snow under your ski melted. And that's providing the grease that you need to ski. Okay? So skiing is only possible because of this negative slope. Had water had a positive slope, you wouldn't be able to ski. Or even if this line were vertical, you wouldn't be able to ski. Okay? So I'll come back to that answer, that question in a next class, hopefully. Okay. So the phase diagrams are extremely important, and you'll see phase diagrams for all kinds of materials. Okay. All right. So here's how absolute zero was discovered. Okay. So you can take a flask, and you can take different amount of gases in a given volume, okay, at the same temperature. And what we'll do is we'll start decreasing the temperature. And what you find is the pressure in the flask will decrease. Okay. And so you see here the pressure. Okay, so the pressure is 40 atmosphere. The pressure is because of these gas molecules bouncing off the wall, and they're exerting a force on the wall. Okay, so when the molecules all stop, the pressure will go to zero as well. Okay, and that's how absolute zero was discovered. Okay, so you see all these lines meet at the same point, at the same temperatures. So the pressure is going to zero at the same temperature. And that's how absolute zero was discovered. Okay. So at absolute zero, all molecular motion ceases, and the internal energy of the system is zero. Okay, so here is the triple point of water. As the name suggests, at this point, there's the triple point of water. So there's the pressure at the partial pressure of water vapor is 0.006 atmosphere. The temperature is 0.01 degrees Celsius. At this point, all three phases can coexist: the vapor phase, water phase, and ice phase. Okay. And it turns out from at this phase, if you change either the temperature or pressure slightly, what you end up doing is you go along these curves. Okay. In principle, you could turn it into any one phase. Okay, so you disturb the system slightly, and you can go to all water vapor phase, water phase, or ice phase. Generally, you end up going there. That's the easiest thing to do. Okay. So from three phases, you can go to two phases or single phase. Okay. So the triple point happens precisely at this temperature and that pressure. And here you can see that there's a vapor phase, liquid phase, and solid phase. So at this point, it's possible to change all the substance to any phase. All right, we'll pause now, take a 5-minute break, and then we'll continue.